Hello, this is Jeffrey Fox here. We're coming on to the third unit on cloud computing, the last unit. This discusses architectures and applications, starting with architectures. And let's get on with it. We are, of course, as we know, using clouds. Those clouds support collaboration, they support the running analytics code, and they process big data, and they solve all these different problems. Problems are what we have to solve. And those problems are sometimes denoted E-X, E astronomy, or sometimes as astroinformatics, X informatics. And here we have our usual collage. So let's first look at cloud and architectures, which we already learned are actually synonymous with effectively large data center architectures. So here we have a slide from Khalidi, who is a key Windows Azure architect, showing how we have what I pointed out before, the fabric controller. It is, if you like, the operating system of the really lowest level of the cloud. Below it's managing all the sets of machines, networks, and computers that make up the cloud. I mean, we have switches and load balancers and things like that. It supports the fault tolerance at this level, identifying bad nodes and switching in new nodes and things like that. It does the mapping of problems onto the physical topology. That's a well-known computer science problem. Everything is done as services, controlling it, and of course we have security in here. Here we have the principles used in building a cloud. The virtualized compute fabric, we just saw a picture of that. The virtualized networking, supporting security and isolation between different applications. We have the scaling out model. We have to support elastic applications. The VIA virtual machine is the unit of capacity. Typically, these are offered in different sizes, different amounts of memory, different number of cores, and they're optimized for mean time between recovery. Each node is a cache. The state must be externalized, stored. We have automation. Everything is run automatically. And we have lots and lots of services which need to be run in a distributed fashion. And as we know, that's hard to do. Here's how Azure does all of this. It uses Hyper-V as the virtualization manager. Xen and KVM are used in the non-Windows world. Of course, now Azure does Linux as well as Windows. I think it still uses Hyper-V. We have virtualized networks, which are overlays on top of physical networks. That's a well-known principle in networking. It's what you saw first, probably in peer-to-peer system. Everything is optimized for the fault recovery scenarios, with different scenarios in terms of cores, memory, and bandwidth, and so on. We have network drives, which are cached on local drives. We have everything automated as services, and we have that's at the control level, and then we have all these higher level. These are platform as a service type level capabilities. So that's all you have to do to build a cloud. And this has all happened incredibly quickly while academia is sitting on its head, contemplating whether or not to change. Companies have just built this. So here are some comments on the challenges. There is not clear agreement on that, but there's some general agreement of percent, somewhere between 1% and 5% of energy is consumed in data centers. I think the disagreement probably depends on what you call a data center. And in 2006, data centers were not efficient. They're probably, I don't know, 3 times as more efficient today than they were in that time. As we pointed out continuously, fault tolerance is essential. You cannot have 100K servers and not have lots of errors. Disks will always fail. And you've got to not only put that into the fabric and the hardware design, you actually have to put it into your software. And your software must be tolerant of failure. It must be able to restart itself. And as we actually had on a different slide in unit 2 of this cloud set of 3, we have 2 forms of parallelism. Lots of users, and for a given user or a given application, lots of nodes to solve a single problem. The second is usually called parallel computing. The first is actually a form of parallel computing, pleasingly parallel over users, but not normally thought of in that fashion. Here we have raining down from the sky. They happen so quickly, you may not have seen it. Let me show it to you again. There you are, they rain down. These are all these data centers raining down. At the top here, we have some highlights. Here's their 4th generation data center. We're just showing in more detail here, where everything is modular. It's not obvious that you even need a actual roof over these, because once we decided to make everything faulty, maybe it's better for us to build these systems in a easier to maintain and scale out and repair state, but in a fashion that maybe with if you go to most universities, including Indiana, there's huge effort is placed into the quality of the data center. Some of these trade-offs in cloud said it's better not to do that, but rather to put your effort into scaling and modularity, and just because you've already been taught how to cope with faults. So if you have something that increases the fault level 10%, probably doesn't matter. You've already learned how to cope with those with 10% with faults. And here we have this magic, an amazing number from 100,000 to 1 million servers. And here is some examples of rather old now actually, with this has here the largest case is only 50,000 servers, and here we have examples here from pictures of warehouses for the servers, where each of them is over 10 times the size of a football field, and you see why they're cheaper. The network is 7 times cheaper, the storage is 6 times cheaper, and the administration, you don't need as many. The people per node is lower in a large center because you have redundant. If everything is the same, you don't need as many people to maintain it. So here the key point is you put them where possible. Here's some in Oregon. You put these warehouses where power is cheap, either because it's really cheap because of hydroelectricity, or because due to tax breaks and things like that, the community which attracted you has made it very cheap. Here's this now a rather old slide of this key idea of building data centers out of containers. So we have up to 1,000 nodes in a single container, and you just construct the container away from the cloud center, and you just truck it up when you want it. And in this now rather old data center in Chicago, they have up to 200 shipping containers filled with computers in that starting off that data center.